Yeah, thank you, Anna, for the introduction. Hello, everybody. My name is Mojtaba. I am from KU Leuven, Belgium. Our research group is focused mainly on biomedical engineering and computational models in tissue engineering. And my PhD work is related to mathematical modeling and computational modeling and some of these processes. And in this presentation, I want to talk about biodegradation behavior of metals. And by biodegradation, we mean the process that you put some materials inside a body and they get absorbed and vanish. So there is no need to do some, let's say, secondary surgery to remove them. So, as I said, the research is focused on metals or different types of materials, metals, plastic, polymers, ceramics. This research is focused on metals, and when we are talking about biodegradable metals, we are usually talking about magnesium, zinc, and iron. These are the most famous ones. And as I said, the main goal is, we want them to gradually disappear inside the body. So, and also, when they disappear, it's not a holy space, it's really something, it gets replaced by tissues or bones, for example. In orthopedics, it gets replaced by bones. And they are metals, so they have great mechanical properties, obviously, and also some biological, interesting biological properties, such as positive contribution to body metabolism. But still, the degradation, the release profile, because this is really material that is released in the body, controlling the release profile is an issue. And then it should be tuned based on different applications, as you can see on the right. So the problem, no. So the challenge is actually tuning the biodegradation behavior or release profile, what they behave inside the body. And then the application is tuning or optimizing the implant shape or the biomedical device behavior based on this kind of investigation. And instead of doing some experiments, some expensive experiments, in this research we're going to do a mathematical modeling of this behavior that can be solved with computational models, and then coupling these mathematical models of degradation with tissue growth models that are very very commonly used in tissue engineering. And then also we should consider the environmental effects while we are developing the models. So as this is very common in this kind of research works, that the workflow is we convert the underlying science, the multi-physics behind the scene to mathematical models, and then these mathematical models to computational models. In this work, the underlying science is the chemistry of biodegradation, because that's a chemical process. And then the perfusion, the physics of perfusion. This is a term that people use in tissue engineering, but it is actually fluid flow that can be inside the body or inside the experimental setup. So the physics of fluid flow and also the biology of tissue growth, because this is also important to be considered. And for converting these things to mathematical models, we use a set of partial differential equations, which are mainly reaction, diffusion, convection equations. And also we need to, as I said, deal with fluid flow. So we have Navier-Stokes and also a couple of techniques to track the interface. I will talk about this. In this case, it is level set and phase fill. And then to solve these equations, we use a combination of finite element and finite difference method, as well as parallel computing libraries and open source solvers. So I will go through this as a very general overview. So I start with the biodegradation framework. If you want to capture the biodegradation process inside the body, the model should consider first the chemistry of the solution of the material. In this case, it is magnesium. In the simplest case, and then formation. This is known as corrosion product. Formation of a protective layer on top of it, slowing down the degradation, and then also the effect of environment on that, like if there are the presence of ions, the solution of this, elimination of this field, and these kind of processes, and also the change of pH, acidity of the environment. To construct a mathematical model, I don't want to go to the detail, but it is really like as simple as converting the chemical reactions that we know, interactions, into mathematical models, as I said, by taking advantage of the fundamentals of reaction, diffusion, convection equations. So just an example for the transport of the magnesium ions inside the body. This is the kind of equation that we deal with. So we have an equation like this for any component that is in a system. So for a typical system, we usually have 8, 9 equations like this. that, as you said, it's actually describes how the ion or the material diffuses in the surrounding environment, how it gets convected by the fluid flow, and how it reacts to the other components in the system. And then we need to solve these equations. This is very common to use software programs with pre-built models in tissue engineering and biomedical engineering, but in this case we cannot do that because we want to have full control, especially at the interface of the material surrounding. I will show you why. So we need to discretize, we need to solve the equations ourselves by discretizing the PDEs using finite element method and finite difference method, and we need also another technique to capture the interface movement, which is actually the interface of the implant as it evolves over time, shrinks, let's say, because it's degrading. And then, because the main part of the investigation is on the interface, we need to refine the mesh on the boundary of the surface, of the corrosion surface, let's say. So the kind of model, the kind of geometry that we deal with is something like this. So it is not really like Lagrangian presentation of materials. This is fully Eulerian. We mark part of the mesh as, like in this case, this 2D screw as the material, and then the surrounding, and then we refine the mesh on the interface. So this is fully Eulerian presentation of the material. And then to implement it, we use a set of tools for mesh generation. The typical mesh, because we usually, as I said, we refine a mesh on the interface, is usually around 20 million of elements. And then for weak formulation, the degrees of freedom for each equation, as I said, we have usually 8-9 equations, is around 4 million. So parallelization is crucial. For parallelization, we use high performance domain decomposition as well as high performance preconditioning and solvers available in PET-C to increase the performance, and also parallel I/O post-processing. So this is a kind of results that we can get. On the left, you can see the screw and the cross section of the surrounding medium. This is the way the material is released, and the medical device or the implant is getting shrinked. And on the right, it is just the interface, which is captured by the level set method. I will show you the details later. This is another type of porous scaffolds that you can see the formation of the protective film on a surface, and then the release of material on the right. This kind of scaffolds are very common in tissue engineering. And that's why we needed to actually have a sort of mechanism to simulate it. And this is a jawbone plate, a mandible plate that is they put for like fractures on a face. And these are new kind of implants that they degrade eventually, so there is no need to remove them after their work is done, actually. And this is a slow degradation over months, and we wanted to see the degradation because we wanted to couple this with a mechanical analysis to get the mechanical failure over time. And this is a benchmark, actually, because we wanted a benchmark to compare with experimental results. This is a narrow cuboid to compare its degradation behavior with some experimental results. Both results are the same. That one is rendered on a GPU, and this is a normal release of material. And then we can capture the change of pH, because this is something that chemists really like to measure, and then this is an important criterion for them to see the behavior, the corrosion behavior of things. So we have here a saline solution, which is in a high rate of corrosion, as you probably know, and then buffer solution when they chemists add different ions, different materials that slows down the degradation rate. And then we have also a set of quantitative results to compare. And in this case, at least for this basic model, we see that we have a good agreement with the experimental results in different mediums. And then we want to add the perfusion, because this is very common in tissue engineering that they have perfusion to study something, because you need continuous supply of materials and removal of waste, and that's why we need perfusion or fluid flow. So for considering convection, we need to add the effect of hydrodynamic conditions. And from the engineering perspective, it means that we need to add Navier-Stokes equation to the whole workflow. That needs actually another kind of solver to couple with the basic model. This one is also implemented in freeform, so no coupling libraries used. Everything is implemented in freeform in parallel, and then we also needed to compare results with another, let's say, less sophisticated CFD solver to be sure that the code that we have implemented works correctly. So this is a kind of experimental setup that we have access to, fortunately, from our partners in Germany. They have a very, very advanced setup to measure a lot of things that are useful actually to compare the simulation output with. And this is the inlet, this is that outlet. And for comparing, like in this case, at least the fluid flow results, we have such a geometry. And then this is the comparison of the solver output with OpenFOAM. As you can see, this is very similar, both qualitatively and quantitatively, meaning that the CFD code works correctly. So kind of verification, and this is a streamlined behavior, although OpenFOAM was much better to capture the boundary elements, but that's fine. We don't care about that. And then when we add the degradation to fluid flow, in this case like a flow from left to right, you see that it actually pushes the release material to the right. And this is the way that we can combine these models. And in order to have a better investigation on what is going on a local, very close, like 50 micron, 100 micron, that distance, to the surface of the material, this is a more detailed model of that process. So we have still fluid flow, but everything is captured in a smaller scale. So this is a kind of results that you can see. This has much more chemical components involved, but in this case, I want to draw your attention to the effect of fluid flow that moves things to the right, and it has also effect on the pH, local pH profile. Local pH means measuring of pH at a distance is very close to the corrosion interface. And this is for another temperature, so showing that the model is able to capture even the effect of temperature on this local pH evolution, which is very interesting for chemists usually. And these are also the kind of quantitative results showing the difference in different temperatures over time. This is in a short time window in 12 hours only. And then the last part that I want to discuss, I want to show you, is a bit of what I meant by tissue growth. So in tissue engineering, you have like, you have this kind of scaffold, we call it open porous, and then they have some nice shape, I would say, but some random shapes, and then they put cells on these scaffolds, and then they start to grow. Like, you can look at it as a way that they develop like artificial organs like ears or fingers when they want to develop something like that. This is the very initial state, cell proliferation they call. And then the goal of the study is we want to see what is the effect of those geometrical properties on the rate of this tissue. So we can use actually these kind of models to integrate with biodegradation model and then see what happens to those biodegradable materials inside the body, because inside the body, the tissue growth is very similar to this. But what is really important is in this kind of modeling, they model the tissue growth as a free boundary, let's say, moving boundary problem. This kind of problems category in mathematics, excuse me. And that's the way that we can model this. So for example, consider this one. This is the void space, and this is the tissue that is growing. It's proved that whenever we have a higher curvature, we have a higher rate of tissue growth. So something like this can be captured easily via a phase field model of level set models. So something like this, using a Heaviside function to capture like the curvature, and then apply that to a phase field model. So in phase field models, it's like this, that we have the void space. When the phi function is positive, is 1, and then we have the tissue when it is -1, and the interface is defined via this transition between these two regions. So if we simulated this with finite element model, it yields to something like this in 2D and 3D. And then this is something that I should have discussed earlier, but I wanted to put it here to make the contrast between these two models, and that's the way that we capture the biodegradation interface when we simulate biodegradation. For that, we use level set method, and this is the equation. This is a typical level set equation, but instead of the velocity, the normal velocity, we have like this correlation that it correlates the mass release to the interface velocity. And in this case, that's a psi function that is defined like 0 on the interface. This is a little bit different from the phase field. Positive or it doesn't matter. It's here negative in the medium surrounding and positive inside the block. And this is the kind of results that it leads to. I showed you this one before. So this blue surface is nothing but the 0 isocontour of the level set function. And then combining these two together is a little bit difficult because we want to have them both at the same time. This is actually what I'm currently working on. So we have the scaffold here. So this is a psi function I showed you before. It's positive, negative, and then we have tissue on top of it. And then this is the phi function as the tissue grows. So we have the movement of the interface. So new region for the phase field function. And then we have the degradation. So the problem is at this moment, we do not have a proper mathematical description of this new formed area because that's a little bit difficult to capture. It's something, dealing with the psi function and the phi function. And then a last note on the software development and the way that we have developed these models is now all of these models that I showed you are combined into the software. So it's a multifunctional 3D simulation code for biodegradation. We call it BioDeg, and it has a cross-platform user interface and has its own pre and post processor. We have made this to for making it easier for people outside of the field to work with these models. It has a free FemPC back end and Qt front end, and is available as open source tools. And all the tools that I use in this research are open source, making it feasible, making it possible for anyone else to grab the code and reproduce the results. And all the things that I showed you are hosted already on GitHub, including the core models, including the degradation, the tissue growth, and the fluid flow. The perfusion. It's called the core, and then the UI is also available in GitHub, and the preprocessor and postprocessor, the documents, also the theories, and then also the coupled fluid flow solver. These are all available on GitHub to be used by anyone else. Thank you so much for your attention.